We have looked at thin layer chromatography, TLC, where the mobile phase is a solvent and the stationary phase consists of silica particles coated onto a glass plate support. In TLC, the substances being separated travel at different speeds up the plate, since those substances that form stronger interactions with the stationary phase are held up the longest and travel slower. We will now look at gas chromatography. With gas chromatography, the mobile phase is a gas, and this flows at a constant flow rate through a column containing the stationary phase. The column can be a piece of glass or stainless steel coiled tubing filled with a loose powdery material which forms the stationary phase. In order for samples to be separated under gas chromatography, they must be in the gaseous phase, and so the column is placed in a thermostatically controlled oven to keep the substances of interest gaseous. When we looked at TLC using silica as the stationary phase, the substances being separated were held up / retained because they were going through a cycle of being adsorbed onto the surface of the silica and then desorbed from the surface. The waxy materials mostly used as stationary phases in gas chromatography work differently, in that the substances being separated partition into and out of the stationary phase. That is, they undergo a cycle of dissolving in the stationary phase and then come back out again. Consequently, substances are separated based on their solubilities in the stationary phase material, with those substances being the most soluble being the longest retained. A small quantity of sample is injected into the flow of the gas just before the column. The substances within the sample are then separated in the column, with the substance that is most soluble in the stationary phase travelling the slowest. In this case, the blue substance. Following separation in the column, the separated substances enter a detector. There are various types of detector, but all detectors work by producing an electrical signal when a substance passes through. This electrical signal is plotted on a time axis using computer software, and the resulting plot is known as a chromatogram. Peaks in the chromatogram show when substances have been detected. The time taken from when a sample is injected to when a substance from the sample has been detected is called the retention time. In a similar way to how RF values are used in TLC to identify substances, retention time can be used by running a sample of pure known substance and seeing if the retention time of the peak observed matches that found in the sample. The size of the peak in the chromatogram is proportional to the concentration of the substance in the sample. Chromatographic software is able to find the area under the peak and use this for quantitation. An analytical chemist, if wanting to know the concentration of a substance in a sample, might weigh out a quantity of the pure standard substance accurately, and then dilute this volumetrically to obtain a series of standard solutions of known concentration. These standard solutions can then be run on the gas chromatography system. The peak areas of the peak corresponding to the substance of interest can then be measured and a calibration graph constructed by plotting the peak area against concentration. If a sample with an unknown amount of this substance is then run, the peak area of the substance in the sample can be measured and the calibration graph used to find its concentration in the sample.